First we will draw transfer characteristics. Transfer characteristics will be drawn between ID and gate to source voltage VGS. Sorry. Negative gate to source voltage is applied and we will see the current ID. In JFET, now if voltage VDS is applied to the JFET, the field will be set up in the channel, and due to this field, charge carriers will start flowing and drain current ID will flow to the device. If VGS equal to 0 volt, this voltage between gate to source voltage. If VGS equal to 0 volt, the depletion layer width will be somewhat like this. It will be more towards drain end and less towards source end. But if we increase VGS in negative direction, means this voltage is made more negative, minus 3 volt, minus 4 volt, then the reverse biasing between this P plus and this N channel will be increasing, and between this P plus and this N channel will be increasing, and with increasing reverse biasing, the depletion layer will penetrate more into the channel. So when VGS equal to 0 volt, the width of the channel will be maximum and the drain current ID will be maximum, that is ID SS. Now if we go on increasing this VGS, gate to source voltage VGS, if we go on increasing this VGS, reverse biasing between gate and drain, reverse biasing between gate and source increases, and with increase in reverse biasing, the depletion layer penetrates more into the channel. If the channel width decreases, the current through device decreases. And for a particular value of VGS, the depletion layer on both the sides will touch each other and the channel will be cut off. Channel will be cut off, and in this case, the drain current ID will be equal to 0. This voltage is called VGS cutoff or VP, pinch off voltage. Or pinch off voltage. These are the transfer characteristics of N channel JFET. There will be similar characteristics for P channel JFET. For P channel JFET, the characteristics will be like this. We will apply positive VGS in order to make gate to source junction reverse bias. Now we will draw transfer characteristics, drain characteristics for JFET. Number 2. Drain characteristics are plotted against drain current and drain to source voltage by keeping VGS equal to constant. Earlier we kept VDS equal to constant, and this time we will keep VGS equal to constant. Now this time we will keep this VGS at a constant value, and we will vary this voltage VDS. If this voltage VDS is varied, the field in the channel will vary. Along with this field, there will be variation in the reverse biasing between drain and source. Only drain and source. If drain and gate. If gate is kept at -2 volt and initially drain to source voltage and initially drain to source voltage is for example +3 volt, then the reverse biasing will be 5 volt. If we increase it to 5 volt, then the reverse biasing will be 7 volts. Means with increasing drain to source voltage, the reverse biasing between drain and gate will be increasing. When VDS equal to 0 volt, VDS equal to 0 volt, the field in the channel will be equal to 0. If the field is 0, then there will be no flow of charge carrier and drain current ID will be equal to 0. Now, if we increase VDS is increased, then reverse biasing between drain and gate will be increasing. Also, the field in the channel will be increasing. So now the depletion layer width can be seen like this. But with increase in electric field, the charge carrier flow will also increase, and at lower voltages of VDS, it is seen that drain current ID increases linearly with applied VDS. Further increase in VDS will further increase the reverse biasing and hence depletion layer width. But with increase in depletion layer width, the field is becoming stronger. This field EV is becoming stronger, and charge carriers will flow with higher velocities and will determine higher drain current, and the current will continues to increase linearly with VDS. At a particular value of VDS, both the depletion layers will touch each other, and in the earlier case, at this point, the drain current ID was reduced to 0. But this time, at this voltage, this field, electric field E, is sufficiently strong to maintain the flow of charge carriers electron through this gap. Means this electric field will not allow both the depletion layers to touch each other. There will be always a small gap between these two depletion layer, and through this gap, this depletion layer will maintain flow of charge carrier and drain current ID will continue to flow. But at this voltage of VDS, the velocity of charge carriers will saturate and they will move with constant velocity and hence will carry a constant current. So at this point, this voltage is called pinch off voltage VP. At this point, drain current ID saturates. At this point, both the depletion layer touches each other, and at this point, this voltage is called VP. Remember that this point, this voltage VP is different from the voltage that was seen earlier. Now, if we change the value of VDS, means we will set VGS at any different voltage and it will be kept constant. So if we set VGS equal to 0 volt, then we will obtain this graph. If we set VGS equal to -2 volt, then we will get same graph, but it will be drawn below, and these will be the curves for higher values of VGS. This curve will be for VGS equal to 0 volt, and this curve will be equal to 0 volt for -2 volt, and this curve will be for VGS equal to -4 volt. These are the drain characteristics of JFET. Now we will see some basic definitions about related to JFET. First, drain current ID. Drain current ID. Drain current ID is mathematically given by ID equal to ID SS into 1 minus VGS upon VGS cutoff. This VGS cutoff is sometimes written as pinch off voltage VP. So drain current ID can be written as ID equal to IDSS into 1 minus VGS upon VP. Sorry, it's square. Now drain current ID depends on square of VGS. If it depends on square of VGS, JFET is called as square law device. It's called square law device. Next term related to JFET will be its transconductance. For JFET, its transconductance GM is defined as GM equal to del ID upon del VGS at constant VDS. We know the equation for drain current ID. It is IDSS to 1 minus VGS upon VT whole square. Differentiating this with respect to VGS, we get GM equal to IDSS into 1 minus VGS upon VT into 1 upon VT minus 1 upon VT. So rewriting it as -2, so it will be 2 into 1 minus VGS upon VT, and IDSS will be equal to minus 2. Transconductance Gm will be equal to minus 2 IDSS into 1 VT into 1 minus VGS upon VT. This will be the equation for transconductance of Gm. Now, in this equation, if VGS is made 0, then the transconductance will be maximum. That is, at VGS equal to 0 volt, Gm will be maximum, and maximum Gm is given by GMO will be equal to minus 2 IDSS upon. So now I can write transconductance Gm equal to GMO into 1 minus VGS upon VT, where this term is maximum transconductance. Now the next term will be drain resistance. This drain resistance is defined as RD equal to del VDS upon del ID at constant VGS. And last term is amplification factor. Amplification factor. The amplification factor is defined as mu equal to del VDS upon del VGS at constant ID. And also it is written as mu equal to Gm into RD. So transconductance and then resistance RD, the product will be amplification factor